All right. So have you ever stopped to think about like how these large language models, ChatGPT, I mean, everyone's heard of it by now. It's like they can just like spit out facts like faster than you or I could ever even like process the question.
Yeah, it's kind of unnerving, right? It's like, do they have like a whole encyclopedia jammed in their digital brains or what?
And that's why we're doing this deep dive today, because I want to get to the bottom of this.
hmm
Where do those facts actually live? Like, how is that even possible?
It really makes you realize like how different these AI systems are from us, right? Like we tend to think in terms of, memory, like our own memories or like a computer's hard drive.
Yeah.
But with neural networks, it's a whole different ballgame.
Okay, so to really wrap our heads around this, we've got two sources lined up. One's a three blue, one brown video. It gets into like the nuts and bolts, the technical stuff. And then we've got this thought piece called The Symphony of Simplicity. It's kind of like a more philosophical take on the whole thing.
Yeah, we need both perspectives, I think, to really appreciate like the complexity, but also the almost like elegant beauty of how these things work.
Okay, so first myth to bust. It's not about memory locations like we're used to,
Mhm.
Like on our computers, there's a file for this, a folder for that. But with LLMs, it's all about what's called distributed representation.
Think of it this way.
All right.
Imagine an orchestra, like a symphony. The melody itself isn't contained in any single instrument, right? It's the combined effect of all of them working together, the relationships between the notes, the harmony. That's what creates the music. And neural networks are kind of like that.
So instead of files and folders, we've got these interconnected nodes called neurons. And each connection between them has a weight, which is basically just a numerical value.
Right. But here's the mind-blowing part. It's not like one weight equals one fact or anything like that. The knowledge isn't stored in any single weight or even a group of them.
Whoa. Okay, so then where is it?
It's in the overall pattern, the interplay of all those weights across the entire network. That's what encodes the information. It's like the network as a whole is learning to recognize certain patterns, and those
Yeah.
patterns represent knowledge.
So it's not like a one-to-one mapping. Like you
Mm.
said, it's more like, okay, let's take an image of a cat, for example.
Mm-hmm.
A regular computer would just store the pixels.
Mm-hmm.
But an LLM, it might break that image down into different features like edges, textures, shapes, and those features could be spread across different layers of the network.
Exactly. It's like the catness isn't in any one place. It's more like a symphony of features that the network learns to recognize as a whole. Like each part contains a hint of the whole.
It's kind of like a hologram, right?
Yeah.
Like each piece contains the whole image in a way.
Yeah, that's a good analogy.
All right, so let's get a little bit more technical here. Three blue, one brown. In his video, he takes us inside what's called a multi-layer perceptron, or MLP. It's like a specialized team within the larger neural network company.
And he uses this really great example, the statement, Michael Jordan plays basketball. Pretty simple fact, right?
Yeah.
But for the network to actually understand that, it needs to grasp concepts like names, sports actions, and how they all relate to each other.
Right. It's not just memorizing a string of words. It's
Yeah.
about understanding the meaning behind them.
Exactly. And that's where embedding vectors come in. Picture them like coordinates in this really crazy high-dimensional space.
High-dimensional space. Whoa. Okay, my brain's already starting to hurt.
Yeah, it's a bit of a mind bender. But basically imagine that each direction in this space represents a different concept. So one direction might be first name Michael, another direction might be basketball, and so on.
So every concept has its own, like, direction in this space.
Right. And the clever part is using what's called the dot product. It tells you how much a vector aligns with a certain concept. So if you have a vector that represents Michael Jordan, it's going to have a strong dot product with both the first name Michael and the last name Jordan directions.
It's like saying, hey, this vector is definitely pointing in the Michael Jordan direction.
Right, exactly.
So the network is kind of like mapping out the relationships between all these different concepts in this really high-dimensional space.
Right. It's building up this intricate web of meaning.
Okay, so three blue, one brown walks us through what actually happens inside this MLP, all the mathematical operations, the matrix multiplication. There's this function called ReLU, which is...
Don't worry too much about the specifics of the math, but the key thing to remember is that this whole process isn't happening for just one vector at a time. It's happening for thousands of vectors simultaneously.
So it's like massive parallel processing.
Exactly. And that's where the true power of these networks comes in. The sheer scale of the computation allows them to process and understand information in ways that we can barely even comprehend.
Okay, so I'm starting to get the picture here. I've got these embedding vectors swirling around. They're getting transformed by all these mathematical operations. But how does that actually become like a fact? Like Michael Jordan plays basketball. How does the network actually make that connection?
So in the video, 3 Blue, 1 Brown simplifies things a bit. He shows how the MLP could activate certain neurons based on the presence of certain concepts. It's like if both Michael and Jordan are strong, it triggers an ND gate and adds the basketball direction to the output.
So it's like the network is saying, aha, this vector is Michael Jordan, and we know he's got basketball vibes. So let's include that in the output.
Exactly. And keep in mind, this is a very simplified example. With thousands of neurons, each one could be encoding different aspects of knowledge. The complexity is what allows for the richness of language understanding.
Okay, so we're already pretty deep down the rabbit hole here, but there's another layer to this, right? 3 Blue 1 Brown mentions this idea of superposition, which suggests that things are even wilder than we initially thought.
Yeah, this is where it gets really interesting. Superposition basically means that neurons aren't just representing single features, but combinations of them.
Whoa, so it's not just one neuron for Michael Jordan, it's like a whole bunch of neurons, each representing different aspects of him.
Right, it's like each neuron is playing multiple notes in the symphony. It makes interpretation a lot harder, but it also potentially allows the network to scale to incredible levels.
Okay, my brain is officially fried, but I'm also super intrigued. So instead of one neuron shouting, Michael Jordan, it's like a whole chorus humming different parts of his identity, his skills, his connection to basketball.
Exactly. And it all ties into this mind-boggling concept of high-dimensional space, which might sound intimidating, but it's key to how these networks can store so much information.
High-dimensional space.
Right.
Okay, you're going to have to break this down for me because I'm pretty sure I'm not the only one who's lost at this point.
All right, so think of it this way. In our normal 3D world, we can only fit 3 lines that are perfectly perpendicular to each other, like the corner of a room. But as you go into higher dimensions, you can fit way more lines that are almost perpendicular.
So more room to play. More ways for things to be connected without overlapping completely.
Exactly. And there's this mathematical theorem called the Johnson-Lindenstrass lemma that proves this. It says you can fit exponentially more of these almost perpendicular vectors in the number of dimensions. So that's partly why bigger models are so powerful. They can handle a much richer web of concepts.
It's like each new dimension adds this whole new layer of meaning that the network can tap into. Which brings us back to superposition. By combining features in these high-dimensional spaces, MLPs can be probing far more than we initially realize, like squeezing every drop of meaning out of those weights and connections.
And that leads us to something really fundamental about both artificial and biological intelligence. It's less about rigid facts and more about patterns, connections, navigating this vast sea of information.
So instead of LLMs being like glorified fact-checkers, they're more like master relationship weavers. They don't just memorize, they synthesize.
Exactly. And that's crucial because it means their learning is fundamentally different from how we traditionally think about it. It's more about statistical relationships, probabilities, than hard-coded rules.
Okay, so we've gotten pretty deep into the technical weeds here,
Mm-hmm.
but I'm also curious about the bigger implications. Like if intelligence isn't about storing facts, what is it about? Then what does that even mean?
Yeah, that's a great question. And that's where the Symphony of Simplicity really shines. It compares the distributed nature of neural networks to our own brains. Like, we don't have specific memory slots for each fact either. Our knowledge, our memories, even our sense of self. It all emerges from the connections between billions of neurons.
So it's not about location, it's about connection. It's pretty poetic when you think about it.
It is. And this constant flow of information, this interconnectedness, that's where intelligence seems to arise. Not just in machines, but potentially in us, too.
Okay, but hold on. If it's all so distributed, how do we even make sense of how these systems work? It feels like they're operating in a black box. We get the output, but we don't really understand the why behind it.
That's the challenge of interpretability. We can build these incredibly powerful models, but even the people who create them can't always fully explain their reasoning.
That's kind of unsettling, right? It's like having a friend who gives amazing advice, but they never tell you how they figure things out. You start to wonder, like, can we really trust something that we don't understand?
It's a valid concern, and researchers are working on developing tools to try and peek into these black boxes. Things like activation visualization, which is like seeing which parts of the network light up when it's processing information.
Right, like trying to get a glimpse into the inner workings.
Exactly.
There's this example in the Symphony of Simplicity that really stuck with me. It's about this AI that can detect tumors in X-rays. But it doesn't do it by understanding anatomy like a doctor would. It's learned to correlate subtle patterns in the pixels with the presence of tumors.
It's a perfect example of how this emergent intelligence can be both revolutionary and a little bit unnerving. The AI gets the right answer, but through a process that's totally alien to us.
It makes you wonder, like, what else might it be seeing that we're blind to? What other
Mm.
patterns are hidden in the data, just waiting for the right kind of intelligence to unlock them?
It really challenges our assumptions about what it means to think or to understand, and it pushes us to develop new ways of interacting with these systems, beyond just feeding them input and expecting output.
Okay, so if we zoom out for a moment, it seems like the real power of neural networks is in weaving relationships, not just storing facts. They're like pattern recognition machines on steroids.
Exactly. The Symphony of Simplicity uses this beautiful metaphor. It's not about a library, it's about composing a symphony. Each weight is like a note, and the melody that emerges is the model's understanding of the world.
And we see this with models like GPT-4 generating text that's eerily human-like, and AlphaFold revolutionizing protein structure prediction. These models aren't just regurgitating information, they're creating innovating.
They surprise us with their ability to connect the dots in ways that we never imagined, and it all comes back to this core principle, distributed representation, emergent intelligence.
Which begs the question, what about our intelligence? Where we just walk in talking neural networks, composing our own symphonies of thought? It's kind of a humbling thought, isn't it?
It certainly challenges that anthropocentric view, the idea that we're the only game in town, the human brain is amazing. But it might just be one example of how intelligence can manifest in the universe. And who knows what other forms are out there. It is. And it's this idea that, maybe we're not so different from these machines after all.
Well, hold on. You're saying that we humans are basically just like walking, talking neural networks.
Well, in a way, yeah. I mean, think about it. We don't have like specific memory slots for every fact we know either, right?
Oh.
Our knowledge, our memories, even our sense of self, it all emerges from the connections between billions of neurons.
Okay, so it's not about like where the information is stored. It's about how it's connected.
Exactly. It's the relationships between things that matter. And that's what these neural networks are so good at capturing. They're learning the patterns, the connections in the data, and that's what allows them to make sense of the world.
It's pretty mind-blowing when you think about it. Like all this complex behavior, all this intelligence emerging from these simple mathematical operations.
It is, and it really challenges our assumptions about what it means to think or to understand. We tend to think of intelligence as this very human-centric thing, but maybe it's more universal than we realize. Maybe it's just a property of complex systems, whether they're made of neurons or silicon.
Okay, so that brings up a really interesting point. If it's all about connections and patterns, then how do we even make sense of how these systems work? I mean, it feels like they're operating in a black box. We give them input, we get output, but we don't really understand the why behind it.
That's the big challenge with interpretability, right? We can build these incredibly powerful models, but even the people who create them often can't fully explain their reasoning.
It's kind of unnerving, right? Like imagine you have a friend who gives amazing advice, but they can never tell you how they figured things out. You start to wonder, can you really trust them?
Exactly. And that's why researchers are working so hard on developing tools to try to peek into these black boxes, to understand how they're making decisions,
Yeah.
to see if we can make them more transparent, more accountable.
So it's not just about building smarter machines. It's also about understanding how they think so that we can trust them more.
Right. It's about building trust and transparency into these systems. Because ultimately, if we want to use AI to solve real-world problems, we need to be able to understand how it's working.
Okay, so there's this example in the Symphony of Simplicity that really stuck with me. It's about this AI that can detect tumors in X-rays, but it doesn't do it by understanding anatomy like a doctor would. It's learned to correlate subtle patterns in the pixels with the presence of tumors.
Right. It's a great example of how these systems can sometimes learn things that we don't even know how to explain. It's like they're seeing the world in a different way than we are.
Which is both exciting and a little bit scary, right?
Yeah.
Like, what else might they be seeing that we're missing? What other patterns are hidden in the data, just waiting for the right kind of intelligence to unlock them?
It really makes you wonder what the limits of AI are. Maybe we're just scratching the surface of what's possible.
Okay, so if we zoom out for a moment, it seems like the real power of neural networks is in weaving relationships, not just storing facts. They're like these incredible pattern recognition machines.
Exactly. The Symphony of Simplicity uses this beautiful metaphor. It's not about a library. It's about composing a symphony. Each weight is like a note, and the melody that emerges is the model's understanding of the world.
And we see this with models like GPT-4 generating text that's eerily human-like, and AlphaFold revolutionizing protein structure prediction. These models aren't just regurgitating information, they're creating innovating.
They're pushing the boundaries of what we thought was possible, and it all comes back to this core principle, distributed representation, emergent intelligence.
Which brings us back to the big question. what about our intelligence? Are we just walking, talking neural networks composing our own symphonies of thought? It's kind of a humbling thought, isn't it?
It is. It makes you realize that maybe we're not as special as we thought we were. Maybe the same principles that govern these incredible AI models are also at play within our own minds.
So as we continue to explore the world of artificial intelligence, we're also learning more about ourselves. It's like the journey to understand AI is also a journey to understand the human mind.
Exactly. And who knows what amazing discoveries await us along the way.
It really is amazing to think about, like all this incredible complexity coming from these like relatively simple building blocks.
Yeah, it's like the whole is greater than the sum of its parts, right? Like each individual neuron might not be doing anything that impressive, but when you connect them all together in the right way, you get this emergent intelligence that can do things that we never thought possible.
And in the Symphony of Simplicity, there's this line that really got me thinking. It says, if intelligence isn't about scoring facts, but weaving relationships, what does that tell us about our own human intelligence?
It's a pretty profound question, right? Like, are we that different from these machines after all?
Hmm.
Are we also just constantly recognizing patterns, making inferences, connecting the dots in this vast web of information?
I mean, it's kind of humbling to think about it that way, right? Like maybe we're not as unique as we thought we were.
Yeah, it challenges that whole anthropocentric view of the world, the idea that we're the pinnacle of intelligence, but maybe intelligence is more of a spectrum, and we're just one point on that spectrum.
So as we continue to explore the world of artificial intelligence, we're also learning more about ourselves.
Exactly. It's like the journey to understand AI is also a journey to understand the human mind.
And who knows what amazing discoveries await us along the way.
Yeah, the possibilities are endless.
So as you continue to explore this incredible world of large language models
Mhm.
and artificial intelligence, remember this. It's not just about the facts. It's about the connections, the relationships, the symphony that emerges from the interplay of simple components.
And if you're looking for expert guidance in navigating this complex and ever-evolving landscape, Shigini Systems is here to help. We offer AI consultancy to help you understand and harness the power of these incredible technologies.
Don't forget to like, share, comment, and subscribe to the Techie Docs AI channel for more deep dives into fascinating AI topics. And until next time, keep those minds curious and keep exploring the boundless frontiers of knowledge.